So yeah, we're doing infinite dimensional Hilbert spaces. And for those of you who were at one of my recitations, we talked about this funny issue that, well, it's just sort of an aside. We'll see later on that the position and momenta operators that measure position and momentum of, say, a particle in one dimension, like its x position and its momentum along the x direction, that these operators, these Hermitian operators, they satisfy this commutation relation that x and p, they don't commute. So they're incompatible operators. You can't have a measurement of both position and momentum simultaneously. Right? And they obey this condition that, x commuting with p gives you IH bar times the identity. And the reason this is weird is if you take the trace of both sides and you sum over all the diagonal elements of the operators, then you can very easily show that for finite dimensions, the trace of any commutator like this, you can just work it out. It's always 0 for finite dimensions. But if you take the trace of the identity, that's just an identity matrix, with IH bar all along the diagonals. If you sum up over all these, the trace of that is, going to be n times IH bar, where n is the number of dimensions. So in a finite dimensional space, having this commutation relation is actually completely impossible. So this whole relationship is impossible if, n, the dimension, is less than infinity. So naturally, in quantum mechanics, the concept of having an infinite dimensional Hilbert space comes up right away. As soon as you try to, get the quantum mechanical version of position and momentum going, you run into trouble. So that's why we're doing it, and it's an important topic. And we'll see some of the differences that you get when you have an infinite dimensional as opposed to finite dimensional Hilbert space. Okay, but I'm going to erase this because it's sort of not really within this is just motivation. Why do we care about this? It's because right away it comes up that you get infinite dimensional spaces. So what's the last thing we talked about is that if you have an infinite dimensional Hilbert space, well, we're always going to consider separable Hilbert spaces, and what that means is that they have a countable orthonormal basis. And this might be contradictory to what you've sort of thought before in undergraduate classes or have been taught, but any Hilbert space we consider, whether finite dimensional or infinite dimensional, any quantum mechanical system, we only ever deal with separable Hilbert spaces. And that just means that the Hilbert space has a countable orthonormal basis, that you can write down a basis of vectors starting with 1, 2, 3, all the way up to, either infinity or, a finite number like spin up or down that we had. But in any case, all the different, systems will consider, whether a particle living on the line or harmonic oscillator, what have you, your Hilbert space is always has a countable basis where you can start counting the basis vectors, and maybe you go to infinity, maybe you don't, but you can always do that. And that's something that's not maybe so obvious when you dealt with, say, wave functions in the past. So, so we'll see. how that works for wave functions. And what's the point here is that if you have a vector that you decompose in a infinite dimensional space, then you're not guaranteed that the sum here of coefficients, it might not converge. So you have to worry about whether or not this decomposition converges to, you know, a vector in your Hilbert space. So that's one of the issues that comes up. And we'll see other issues that come up. So I'll put various issues that come up in infinite dimensional land in blue, I guess. But let's write down some examples for now of infinite dimensional Hilbert spaces. So there's three primary examples that we ever consider, and there's a theorem that says that any Hilbert space, any two Hilbert spaces with the same dimension, if the dimension of one Hilbert space, you know, is equal to the dimension of another Hilbert space, kind of like how we had for the photon polarization and the spin 1/2 particle. Those are both dimension 2 Hilbert spaces. If you do find two Hilbert spaces, you know, that have the same dimension, then you can map any vector in one of the spaces to a vector in the other space. We say that the two Hilbert spaces are isomorphic. So they're the same space in a sense. You can take any phi that lives in here and map it, you know, 1-to-1 to a phi that, you know, lives in here. So that's something to keep in mind. So when I say examples of an infinite dimensional Hilbert space, as long as it has this countable orthonormal basis, it turns out that all of those Hilbert spaces are the same thing. So, you know, the Hilbert space associated with a particle living on a line is the same as the Hilbert space of a particle living on an interval, same as the harmonic oscillator Hilbert space. They're all the same Hilbert space. So that's also not obvious, and we'll sort of think about that later on. But let's do the three examples are, well, the first example is the little L2. That's a space, and little L2 is sequences of complex numbers, infinite sequences. And so, you know, this is just the kind of easy thing. It's directly related to this basis. Any phi in this Hilbert space is, you know, just an infinite sequence, you know, from 1 to infinity of the complex coefficients associated with, you know, the expansion of the vector into the basis. And it's these coefficients, provided that the norm is finite. This is an important thing because, you know, we have this caveat that that the vector might not converge. And everything is fine so long as the norm of this vector, right, is finite. So the space L2 is the list of complex numbers, which are these CNs, such that the sum of all the CNs, their magnitude squared, is less than infinity, so that this infinite sum doesn't blow up. That's enough to make this a good Hilbert space where, for instance, you can have a linear combination, right? We have to check to make sure that linear combinations also have finite norm, right, and live in this space. So if you have like a linear combination of these coefficients, where lambda is some complex number, and you look at this squared, you can multiply this out, and what do you get? Well, you get the number plus times its times its complex conjugate, right? It's these usual complex number multiplications. So you get the magnitudes of the numbers squared. And these guys are okay because we'll assume that, we're assuming that each of the individual pieces is finite, gives you a finite sum. So then you just have twice the real part of C and the cross term, lambda star dn star. You can just work that out from the cross term. You get plus this cross term, and you can write that as twice the real part of this complex number. And of course, this whole thing is going to be less than or equal to twice twice Cn squared plus lambda squared dn squared. And you can work that out for yourself by just recognizing that if you have this must be greater than or equal to 0. So you can use this and expand it out and conclude that this thing must be less than or equal to twice these diagonal terms. And we know that each individual one, sums up to something less than infinity. So we can sum over n here, put sums over n, and this whole thing is going to be less than infinity. So it means that if, these two vectors, phi 1 Cn, and I'll draw sum over n, and phi 2, which is sum over n, the dn's. If these are both in your little space L2, meaning they have finite norm like this, then their linear combination phi 1 plus lambda phi 2 is also in L2. That's all we showed here. And you can just show that with just some application of these inequalities. So that's a space. And, we have an inner product. We also have to make sure that the inner product works okay, right? And the inner product in this case is defined in the usual way. If we have two vectors, right, we can just use that orthonormal basis. The magnitude of this inner product is just sum over n, 1 to infinity, of dn star cn, where these are the coefficients of chi and phi. And Cauchy-Schwarz still works, so this is going to be less than or equal to the magnitude of the chi vector times the magnitude of the phi. I'll put double lines. So this is Cauchy-Schwarz. That still works in infinite dimensions. And we're assuming where our space is constructed that all of our vectors have finite norm in there. That's sort of, again, the definition of this L2 space. It's all sequences such that their sum of them squared is less than infinity. Then this must be less than infinity also. So we're good to go. We'll have nice finite inner products between any vectors in this space. So that's the space. It's the space of all complex sequences with, if you sum up their squares, that it doesn't blow up. And if you do that, then you still have a nice vector space where you can add the vectors together and you get something that doesn't blow up. You can take an inner product between vectors and that doesn't blow up. So you get nice stuff. And this is kind of the most natural, I guess, example, because this is the one that's most closely related to what we've looked at before with the finite dimensions, right? We had this basis of finite, 0, 1, 2, 3. base, or 1, 2, 3, however many dimensions. This is the same thing, except now you have an infinite number of them, and so your vectors are infinite sums over the basis vectors, and you just have to make sure that the sum that you get is, doesn't make the vector blow up. That ensures that your vector stays within the Hilbert space. Okay, any questions about that example? That's probably the most important one in some sense, at least mathematically. No? Good. Okay,
I have a question.
Yes.
Under the linear combination title.
Yes.
So on the left-hand side, well, you have the Cn squared plus the lambda squared dn squared plus twice the real term, right?
Yes.
And then you say that's less than or equal to Cn squared plus lambda squared dn squared?
It's less than or equal to twice.
Okay.
Twice.
That's a little confusing to me, but I will prove that.
Yeah, you can check it. It comes directly from this.
Okay,
You can show that this number is bigger than or equal to twice the real part of this stuff. Yeah, I agree. It's maybe not so obvious, but if this number is bigger than this number, then this whole thing must be less than twice that bigger number.
That's true. Yes, that part is less than the other. I can see that.
And this part just comes from the fact that this has to be a positive number. I mean, it's the same thing as we sort of. If I expand this out, right? This is Cn squared plus lambda squared dn squared plus twice the real part of Cn lambda star dn star. This has to be greater than or equal to 0 by definition.
No, that's minus, right?
Oh, yes, minus now. Yes, minus. It doesn't actually matter because the real part can be plus or minus. But yeah, minus because it appears a minus sign. Yes. And so you flip this over to the other side and you get what I wanted, that this thing is less than or equal to twice the real part of this thing. Right?
Greater than, yeah.
Yeah, so then this whole number must be less than twice the big, if this is bigger than that, then the whole thing is less than twice, the big number.
Oh, okay, makes sense. Got it. Thank you.
Okay, great. That. Yeah, this is sort of within the realm of these Cauchy-Schwarz-like arguments. Yeah, this kind of stuff comes up all the time.
Yeah, sounds good. Thank you.
So it's good. Yeah, it's good. It's good to catch me, and yeah, it's good to ask me questions like that. So yeah, please do that. That's great. Any more? So that's an important space. And remember, all these spaces are the same thing, even though they don't seem like it, but they are. Space 2 is one you're probably going to be a little more familiar with. That's the space L2 on an interval A to B. And what this is, it's the space of all square integrable functions that live on an interval from A to B. So you have some x, you have some a from A to B, and it's the space of all functions, or any kind of function in here. So it's the space of all square integrable functions on some interval. They're complex functions, of course. These are the wave functions. And what I mean by square integrable, if you integrate them from A to B, right? Dx, and you take your 5x squared, that's, well, that's less than infinity. Now, this is where it gets confusing for a lot of people because, you know, you can imagine that there's like so many different kinds of functions. You could continuously deform one function into another function. And it's still the case that this space is the same as example 1, where it's just sequences, an infinite sequence of complex numbers. So can anyone tell me what is the relationship between a function on an interval and a sequence of complex numbers? Is there some way which we can map one to the other? So any ideas? If I gave you an infinite sequence of numbers, how would you turn that into a function, or vice versa?
Based off of an angle?
Say again?
Basically based off of an angle in a way.
Okay, maybe. What kind of angle?
So can you repeat again exactly what a sequence of numbers between some set of...
I said up here that if you have two Hilbert spaces with equal dimension, right, then you can map any vector in one space to a vector in the other space. And now I'm giving you 2 examples of Hilbert spaces that are actually the same thing. One example is sequences of complex numbers, infinite sequences, where a vector is written as a sum of complex numbers, you know, 1 for each basis vector. Then I told you that this other space, which is the space of all square integrable functions, take any function you want as long as you square it, you square it, take the magnitude squared, integrate it from a to b, that gives you something less than infinity. And so then your Hilbert space is composed of all functions that are like that, you know. Those are your vectors. What's the mapping between this vector, you know, I could call it maybe 5x, and the, you know, collection of coefficients Cn? How do I get from one to the other? I guess it's a hard question if you're not familiar with this kind of thing. But.
So you're saying a set of functions on the interval from a to b, so all the complex numbers?
It's any function that's square integrable on a to b. Any such function can be mapped, a one-to-one mapping, to some sequence of complex numbers. Conversely, if I give you a sequence of complex numbers, I can tell you what the function is. Any takers? What this is? The mapping.
I guess nobody knows, including myself.
All right, well, I'll tell you. The mapping is Fourier series.
Oh, you just got done talking about that.
Yeah. Oh, and math methods. Yeah, I hear there's some overlap with what I do with math methods. Does anyone know what the exact overlap is for those of you in math methods? You guys did something similar, I guess, that we did or something?
Oh, not this. No, no, I was talking about a different class altogether. That was looking at that. And you were also talking about it earlier, I thought, too, in one of our classes.
Yeah, I think we're starting complex analysis next week.
For the math methods
did you do Fourier
class,
series or anything on Fourier transform?
that doesn't come until the end of the math methods class for us here.
Well, okay. That's okay. Well, for those of you who've seen Fourier series, that's good. For those who haven't, well, just any function I can write as a sum from, well, in this case, we'll include the negative integers, but it doesn't, you could define it in various ways with this ranging from 1 to infinity too, but the general way that you would find in math books is some complex coefficients, and then you have these basis functions, which are, you know, the like sines and cosines for the Fourier series. And in complex notation, it's 2 pi I times n times x divided by the size of the interval, which is b minus a. And conversely, you can find any coefficient Cn by calculating the following integral. Maybe we'll talk about Fourier. Well, my plan was to talk about, you know, Fourier series in recitation a little bit, but anyway, so I guess most of you haven't seen this. I'm not sure, but I would review it. I sort of expected people to see Fourier transforms, at least in some form.
Yeah, I've seen Fourier. There, it's everywhere, usually.
Yeah.
Yeah, we've seen it. It's just wasn't outright clear that was the transformation we were looking for.
Correct.
Yeah.
Okay. All right.
I think
All right.
Well, I saw it in math methods class, of course. I did take that class. But am I good at it? That's the question.
But you see, if you have a finite interval like this, then you can decompose any function into an infinite set of complex coefficients. And each of those coefficients is, you know, the Fourier mode, the nth Fourier mode. And that's the mapping. You can take any function, map it to a sequence of complex numbers, take any complex number and, you know, any sequence of complex numbers and map it to a function. So that's the mapping. It's one-to-one. And that's how these spaces are really the same thing. And the third example is really not obvious, I guess, but it's the one that I guess you would study in math methods most frequently, and it's if you let these A and B intervals get extended out to, you know, minus infinity to infinity. And if you do that, then you get the space called L2R, which is the space of square integrable functions on the entire real line. So this is space of square integrable on, you know, the real line, the whole. And that one's maybe not so obvious, but we'll see, for instance, when you have the harmonic oscillator, right? For those of you who did harmonic oscillator in undergraduate quantum mechanics, hopefully most of you, you remember that you found that, you know, you found the wave functions, right? You found the energy levels of the harmonic oscillator, right? There's the ground state, and then, you know, you did, so the harmonic oscillator is a particle that lives in this kind of, you know, harmonic oscillator potential. And in undergrad, what you do, you know, you solve for the energy levels, and you get these evenly spaced energy levels for the harmonic oscillator, and each one of these is associated with the function. There's the ground state, and, you know,
First excited state, second.
yeah, and maybe if you remember, these things had something to do with Hermite polynomials. We'll see all that too, but you know, there was an infinite set of them. You know, one for each integer. You know, the ground state, first excited, second excited, so all the way up. And those, by what we've learned here, those are functions. They're defined on the entire real line. They're square integrable. And there's, you know, an infinite number of them, but it's a countable infinity. It means that you can actually write any function at all, any square integrable function on the real line as a sum of complex coefficients multiplying the harmonic oscillator. The harmonic oscillator wave functions. And so that's the mapping there. You can map, say, using the harmonic oscillator basis, if you wanted. You can map any square interval function on the real line, which is any wave function, to a sequence of complex numbers. And that sequence could be like the decomposition of that function into the harmonic oscillator wave functions used as a basis. So they're all connected. It's all the same space. You can map sequences of complex numbers into spaces of functions, into a function, and so on. And all you need to do is just identify, you know, again, it's the usual thing. We're always working with Hilbert spaces that admit accountable infinite basis. So in this case of the harmonic oscillator, you could use the basis could be the, you know, the wave functions of the harmonic oscillator, the ground state first excited. Those could be the basis of functions that you can use to represent any function, any square interval function, because, you know, that's the relevant space, Hilbert space for, say, the harmonic oscillator. It's a space of square interval functions on the real line. Any state of a of such a system could be represented as a square interval function, which you can then decompose right into a set of infinite coefficients, one for each, you know, harmonic oscillator mode, if you want. Or you could do the same thing with Fourier series. So, and we'll see more of that later, but there's something to keep in mind that all these things are the same. That's sort of the take-home message here, is all three examples are the same space. You can have a mapping from any function to any sequence of, you know, to some sequence of complex numbers and so on. Okay, any questions about that? It's only one space. There's only one infinite dimensional Hilbert space they have to worry about. It connects all the different kinds of problems we'll look at. Scattering problems, harmonic oscillator.
Now, I do have a question now. I know if I remember, I could be, you know, in math methods, they taught us in this same kind of Fourier series or this test that you don't have to know what's inside the object. You can derive it from this, I thought, from the on the outside, and you can work it from the outside in and go back and forth and get the answer. Does that have the Fourier transform? I mean, can't you transform it one way or the other to be able to get the answers for this particular Hilbert space, or do you have to be within the Hilbert space? You know what I'm saying? Can you, isn't there like subspaces that you can figure out just by being in this space, or no?
Oh, you have to be,
Because you know you got complex and non-complex planes, so I'm just.
No, it's very important that you stay within the realm of nicely behaved functions. Otherwise, you might get in big trouble. It's very important that this, so there's, of course, these are all related things. We said here that the sum of the complex numbers has to be finite.
Mm-hmm.
And we also said that for these functions, that, you know, this has to be true, that they integrate to something that doesn't blow up. That's very important. Otherwise, you're not guaranteed that all of the different spaces, you know, map into each other. If you pick some bad function that's not square integrable, then you might not have this nice mapping, you know, between function and some decomposition, you know, so that you get a sequence of complex numbers. That might not happen. This is only true for square integrable things. So this is very important, that you have to remain within the Hilbert space. And we will venture a little bit outside of the Hilbert space when we talk about eigenstates. which is what we'll do next. But yeah, that's an important point. In order to have this mapping using the Fourier series between the coefficients and the function, it has to be just for square integrable functions. Otherwise, it might not work. So yeah, you have to remain within the Hilbert space for all this to work. Okay, more questions. All right, I'm going to clear this then. Talk about operators. Now, operators are, it's even trickier. So you can imagine, so let's look at this little L2 space and let's look at some vector, right? And again, a vector here is a sequence of complex numbers. Let me just write out, some sequence, C1, C2, C3, and so on, right? Up to infinity, it's just some sequence. And suppose we have an operator A that, say what it does to this phi is it takes each sequence term and multiplies it by its index. So this becomes C1, and this becomes 2, C2, 3, C3, and so on. And this sequence, we know that here we have that, the sum over n of these Cn squareds is less than infinity. But if we do this, then maybe, if we sum up the coefficients of this new vector, maybe this goes to infinity. And, then we're in trouble and this is no longer in our Hilbert space. So just because phi is in your Hilbert space doesn't mean that A acting on phi for an arbitrary operator is. And that's the main issue with operators, that sometimes when you take an operator and you act on your state vector, you might run into trouble. For a function, an operator might be something like multiplying by x, right? Or it might be like taking a derivative. This could be an operation that you do on the function. This spits out another function, but it's not guaranteed that that function is square integrable, right? Just because phi is square integrable doesn't mean that the derivative of phi is square integrable. So you run into trouble. So you have to make a new definition. We say we define the domain of any operator. We could script D sub A. And what that means is it's just the set of all vectors in your Hilbert space such that A acting on that vector is still in the Hilbert space. And moreover, if this domain of A, if the domain of A is equal to the whole Hilbert space, then we say that A is bounded. Why is that? Because because then we can just look at, say, we can define a norm of A. It's like the size of the operator. And that is just going to be the least upper bound, or the supremum. It's called over all states in your Hilbert space such that the norm of the state is 1. So overall normalized states of just the magnitude of A acting on phi. So this is the least upper bound. It means you take all of the states that are normalized, phi is equal to 1, and you look at the value of, you take A and you act on phi with it, and then you measure the magnitude of this vector that results, which is still in the Hilbert space, and you just find the least upper bound of all of these numbers, the norms, and that gives you a sense of the size of the operator itself. And that's what we mean by bounded. It's like the size of the operator when we act with it on a vector it's bounded, and it has to be that way because, you know, because the domain of the operator is the entire Hilbert space. We can act with the operator in any state in a Hilbert space. So, and of course, most operators are not bounded. So we could do some, you know, examples. Say our operator is, you know, the derivative on, say, the L2 space on the interval going from 0 to 1. So if you have some function, and say our function here, our vector, state vector is like the square root of x. This is, of course, this is square integrable on that interval from 0 to 1. But if we take the integral from 0 to 1 of a acting on the square root of x, this is a acting on, you know, phi of x if you want. If we look at this thing, this magnitude squared, right? What we get is take the derivative, get a factor of a half, right? You get 1.5 squared is a quarter. You get the integral from 0 to 1 dx of 1 over x, because the derivative gives you 1 over square root of x, you know, 1 over 2 square root of x. You square that, you get a 1 over x. Uh-oh, this is infinity. Right? You get a log 0. So, you know, then this operator is, we say it's unbounded, right? Because clearly it can act on a state in your space and spit something out that's not in your Hilbert space anymore.
So you're basically showing us a way to make sure that our operators are bounded or unbounded. If they're unbounded, according to the definition that you gave us for this particular Hilbert space, since we have to stay within it, then it would say unbounded, and we couldn't use that operator. We'd have to throw it out and try something different.
No, it's just that operators either are or are not bounded, and most of the operators we'll be interested in quantum mechanics are in fact unbounded. It's perfectly fine. It's just you have to be careful. There will only be a certain domain, a certain subset of your Hilbert space on which the operator can act, right? And still get you something that's in the Hilbert space.
So operators can be bounded or unbounded, but for them to act on a state, it has to be a subset of the operator.
The state has to be in the domain of the operator, yeah.
So for instance, that example you gave us, we would have to take some subset of those numbers in between 0 and 1. And because those are our bounds, those are our states. Could we use that one because it goes to infinity, but we could use some subset to make, because it would just say as long as x doesn't equal 0?
No, for this example, you would just pick some other function that's not that. You'd pick
Oh, so
phi of x is equal to just x. That might work. Take the derivative of x, just get 1.
Okay, so we can never change this one though somehow because of that. There's no way to change it.
It just means that this state vector is not in the domain of A. This is not in the domain of A. So that's what it means.
Well, yeah, I understood that part, but I was just saying that I was just trying to see if we could modify it to get it into that domain for our Hilbert space, you know, but we just have to pick a different one.
A domain is, this is unique. This is a domain of an operator. It's a subset of your Hilbert space, and it's fixed. You can't modify it. You can extend your operator and find some new operator B, and then it's possible that the domain of B is, you know, bigger than the domain of A, and this is called an extension of A. If these operators are equal in the domain of A, say. So you can sometimes find another operator that's the same as your first operator in its domain, but has a bigger domain than your original operator. That's called an extension. And I'll give an example of that briefly later.
And this bounded, the operators being bounded or not, this only comes into play when we are dealing with infinite dimensional Hilbert space, or?
Yes, yes. In a finite dimensional Hilbert space, as long as your operator is, linear, it always spits something out that's in your Hilbert space.
And that's guaranteed for finite dimension.
Yeah, that's right.
Okay, all right.
That's right. Good question. Yep. Finite dimension, everything is okay. You always have bounded operators. So another example maybe is this commutation relation. Which we'll look at a lot. If we examine this thing, this operator over here, this is the domain, right, of this operator, the domain of the identity, that's just going to be the whole Hilbert space. I can multiply any function that I want by IH bar. It's not going to do anything to its square integrability, right? But this, on the other hand, the domain of this commutator is definitely not the whole Hilbert space. It's smaller. You can't just take any square integrable function, and we'll see that P takes a derivative of a function. We'll see that later. But in some sense, when people write this kind of thing, this equality, this commutation relation, they don't really mean this, at least mathematically speaking. But of course, you'll never see this in a physics textbook unless it's a particularly mathematical one. But the more proper thing to say is that, this is an operator, right? And it's equal to the identity, but only on its domain, right? It's an operator and has some associated domain. And it's equal to IH bar times the identity only on its domain. So more properly, maybe instead of an equal sign here, you would put a subset sign, meaning that, this operator is equal to this one, which is another operator, but it's defined on the whole Hilbert space because it's just like multiplying by a constant. This is only true on a special class of functions, right? The class of functions that is in the domain of this commutation relation. So something to keep in mind. This idea of the domain of an operator is very important. So this leads to, okay, so that's one thing, this domain issue. Another thing is the concept of left and right inverses has to be kind of, you have to be careful with it. What I mean by that is just because A times B is equal to the identity, in infinite dimensions, you might have that B times A is not equal to the identity. You might have that. And this is even a part, this is not even related to whether or not an operator is bounded. And we can give an example of this. I like this example a lot because it's sort of really weird. So suppose we have two operators, and we're going to work in the space little L2 of the sequence of complex numbers. Again, this is like the basis decomposition. Say you have A that takes your sequence of complex numbers, right? And say what it does is it just lops off the first term. And it gives you another sequence, an infinite sequence. Now that starts with C2 and then goes to C3 and so on. So, this is perfectly bounded, right? If this vector is bounded, then certainly this vector where you just lop off the first term, that's going to be bounded. I mean, that's going to be a finite norm too. So that's, A is bounded. And we have another operator B And what this guy does is it takes your infinite sequence to and so on. And what it does is it just adds a zero. Zero. C1, C2, and so on, off to infinity. Also must be bounded, you know, just by adding on a zero there and like shifting all the terms over. If all of these guys, you know, sum up to something less than infinity, then of course adding zero is not going to do anything. So, you know, these are funny operators that don't, you know, necessarily have any physical interpretation, but they're just something you can do. It's a way of mapping a vector into another vector. And you can, you know, show they're linear and everything. But so you can check this out. You can check out BA, right? What does this do as an operator on your sequence C1, C2, and so on? So what does it do? So first A acts, right? We know, you know, operators act in order. And so the first thing it does is it lops off the C1, right? And then the B sticks in a zero, right? And so the combined effect is just to replace the C1 with zero. So you get 0, C2, C3, and so on. So, okay. But then what about AB acting on the same thing, C1, C2? What does this do? Well, B acts first, and what it does is it puts a 0 in and then shifts everything over. But then A comes in and just lops off the 0. And so you get C1, C2, C3, and so on. And look at this. That's just, so A times B gives you the identity. It just spits out the same sequence. But B times A is definitely not the identity because, you know, it replaces the first coefficient with 0. So, you know, so you just have to check these things separately. That just because you found two operators that multiply to give the identity doesn't mean that, you know, if you exchange them, the order of operations doesn't mean that you get out the identity necessarily.
Isn't that related to whether they commute or not?
Sure, it means they don't commute. I mean, that's just because the product of operators is the identity doesn't mean they commute in infinite dimensions. That's right. In finite dimensions, it's, you know, this doesn't happen. They're guaranteed to commute, and if you find, you know, the left inverses, it's called of B, then you're guaranteed that if you reverse them, you also get the identity. Yeah, so something to think about, right? And, you know, this is another kind of caveat. And related to this, of course, Hermitian conjugates are more complicated because you can only really so remember, Hermitian conjugate is defined as you know, the Hermitian conjugate of an operator is related to, if the operator acts on the ket, then the Hermitian conjugate acts on the bra. And you have this relationship. But for unbounded operators, it's not always clear that A acts on the same set of vectors as A dagger does. And in fact, the general condition is that the domain of A is actually smaller than the domain of A dagger. And I'll show you an example of this. So in other words, what typically happens is that A dagger as an operator acts on a wider set of things than A does. So you can only really say that, you know, A is equal to A dagger for like Hermitian operators. That's only really true on the domain of A. if you have unbounded operators, and we generally will have unbounded operators. So the whole thing I was talking about earlier about self-adjoint versus versus Hermitian, it can be summed up in this notation, right? That A is typically, subset of A dagger, meaning these are equal on the domain of A, but A dagger might have a bigger domain. That's called Hermitian operators. And the one where they're equal on the whole Hilbert space, that's called self-adjoint. And these are typically going to be bounded operators too. So a little bit of a subtlety, and this it's not very helpful, but it's just something to keep in mind. But I think an example will probably show you what I mean by this.
I didn't know that. I always thought these two are the same things.
Yeah, same.
Yeah, they're
Yeah.
not quite the same. They're not quite the same because sometimes the dagger might act on a bigger space of things.
Is this true only for the infinite dimension though, or even finite?
Yes, only infinite dimensions, yeah.
Okay, that makes sense.
Oh,
But infinite dimensions is really important because when you do like undergrad quantum, all you do is talk about wave functions, right? And you solve Schrodinger's equation in a well, and you talk about the free particle. So all of those are infinite dimensional Hilbert spaces. And how originally, the way this developed, this idea of Hilbert spaces and so on, was people wanted to solve differential equations. And the differential equation, like Schrodinger's equation, they wanted to like have a good handle on like the space of solutions. And so this was very important, these infinite dimensional spaces, because these are the spaces of solutions of differential equations, right? Your operators are the derivatives and so on, and your space of functions, like your L2 is sort of, it's meant to be, the space of solutions to some differential equation. That's what the motivation was for mathematicians to look at this, and so that's why this is important, is because in quantum mechanics we solve differential equations all the time when we're doing particle in a box, scattering, what have you. And it's important to like know what the space of solutions is for those. So that's where all this comes from. All these spaces comes from the theory of differential equations historically. But okay, let's do an example where I'll show you where the Hermitian conjugate sort of breaks down. And we're going to work with L2, 0, 1, space of square integrable functions from 0 to 1. And we're going to have our operator be a sub 0 here. It's going to be minus I times the derivative with respect to x. So the domain of A0, right, it's like the space of it's the space of functions with square integrable derivatives. The derivative of the function is square integrable, then we're good to go. Square integrable derivatives. And it's more than that, though. You can specify the domain further. So this is an important thing. Whenever people tell you, you have some operator like this acting on an infinite dimensional Hilbert space, like a space of functions, there's usually implied in there something else. First of all, this is sort of assumed, right? If your operator is going to be a derivative, then it better act on functions where if you take their derivative, they're still square integrable. But usually as part of the domain specification, you also specify something about the boundary conditions. So your domain is, and this is part of the definition of an operator, is, you specify the boundary conditions of the functions that you're going to be operating on. And so one specification you could do is just arbitrary. It's just one that I chose. This is why you put a little subscript 0. I'm going to say this acts on functions only that satisfy these boundary conditions, right? So this operator only acts on functions that vanish at the endpoints of the interval. you do that. That's part of the specification of the operator. And you can see where this theory of differential equations comes in, because, you know, now your operators are derivatives and they're the boundary conditions. And, you know, as you know, boundary conditions are important for establishing solutions of differential equations. But for us, is beside the point. Is just an example of an operator acting on a space of functions, and we're specifying its domain, that it only acts on functions with these boundary conditions. So let's check out what, you know, this inner product is. And this will also give you a flavor of how inner products and things work in spaces of functions. So this thing must be, the inner product is going to be the integral over the interval dx. And it's the usual thing where you take the bra, so you star it. So you take the complex conjugate of that function of x here, and you multiply it by the operator, which we said is minus I ddx, acting on phi of x. And so we can write that, we can pull out the minus I, we can write this as the integral from 0 to 1 of dx chi star of x and phi prime for derivative of x. And now, what else can we do? We can check the kind of Hermitian conjugate relationship, right? We can check that. We can check this A0 phi. No, sorry, A0. Yeah. We can check the reverse. We're basically checking whether or not, you know, is the question here is this A naught Hermitian? So we're just checking what A naught does when acting on the bras and the kets. It's just seeing what happens. And it's good exercise also for, you know, practicing how these derivative operators work. So if we do this in the other order, right, what we would do is we take the integral from 0 to 1 dx, and now we take the operator, which is minus I ddx, acting on chi now of x, and we star that whole thing. That's the bra part. And then we multiply that by phi of x, right? And if you take the star, then the minus I becomes plus I. So you get I is equal to 0 to 1 dx. And now it's chi prime of x star phi of x. And so, of course, so this is the derivative, and this is complex conjugate. That's fine. We can ask, are these things the same or not? And to try to connect these two things together, you can use integration by parts. And just to remind you, integration by parts comes up all the time when working with these inner products of functions. Integration by parts just tells you that the integral from a to b of ddx, some product of functions, fg, say, which this is fundamental theorem of calculus, it's fg, that product evaluated from x is equal to a to b, that's equal to the integral from a to b of f times dg dx. This is just the integration by parts, just like the product rule for derivatives with just an integration attached. So you can flip the derivative from g to f, right, at the price of introducing this boundary term, where it's the product of the two functions evaluated at the two endpoints of the interval. Just taking little dx's here. It's very important to get used to integration by parts and flipping derivatives around from one function to another, because, you know, you're always taking inner products between functions, and oftentimes these functions have derivatives acting on them, and you want to flip back and forth, you know, the operator between the bra and the ket. And in the function space land, flipping an operator back and forth between one side and another is integration by parts. So in function space land, integration by parts is equivalent to Hermitian conjugate. So it's how you flip operators from bras to cats typically, because the operators will be derivatives typically of some sort. So that's the analogy. So let's look at this. So this then, right, I can write as chi star x phi x. This is that boundary term evaluated from 0 to 1 minus I integral from 0 to 1, where the derivative is flipped. It's dx, and now you have chi star of x phi prime of x. And what did we learn is, look at this. As long as phi of x satisfies the boundary conditions that, you know, it vanishes on the endpoints, then this whole term vanishes and you just get minus I integral from 0 to 1 dx chi star x phi prime x, which is equal to this guy, which is equal to chi a naught phi. So a naught is a Hermitian operator, because we just showed that on the domain of a naught, right, where it includes this boundary condition, on that domain, this is equal to this. But if you look carefully and you look at what happened when we did this integration by parts, if you look over here, see this chi? As long as chi, you know, is, as long as phi satisfies the boundary condition, chi might not. Chi can actually have some other boundary conditions. In general, it doesn't have to be equal to 0 at the boundary points. It doesn't have to be. So if we go back here, this condition that these two are equal is independent of the boundary conditions on chi. And so in fact, and we know that this, right, that's the definition of the Hermitian conjugate. So the operator A dagger here, its domain, which is the set of chi's, is going to be bigger than the domain in which A naught acts, because we saw that the dagger piece, that the chi doesn't have to have that boundary condition in order for this Hermitian conjugate thing to work out. So this is not a self-adjoint operator, as it turns out, because the dagger of the operator acts on a bigger space of functions than the original operator. It doesn't have to have this special boundary condition. So that's kind of something to keep in mind, that in these function spaces, it's important to consider what your boundary conditions are on the function when acting with an operator such as a derivative. We'll discuss this more later, as I'm sort of out of time now, but I guess next thing we'll do is talk about spectral decomposition. That's really the heart of the physics, I guess, related to these infinite dimensional spaces, is what do you do if you have an operator, you know, what is its spectrum? What about the eigenvalues and eigenvectors? How do those work out? We'll see that in infinite dimensions, your eigenvectors can live outside of the Hilbert space. So that'll be something interesting we'll do next time. But hopefully, at least to give you have a sense that, you know, infinite dimensions is subtle. You have to be really careful about when you're acting with an operator, if what you're getting out, whether or not it's still in your Hilbert space or not, and make sure you're sort of properly defining the space of vectors or functions, right, on which you're acting. That comes up pretty often. And this is the way you connect all the stuff we've been doing with Hilbert spaces and so on to what maybe you're familiar with undergrad, which is just, you know, solving for wave functions. A wave function is a complex function, a square integrable function. It's an element of this infinite dimensional Hilbert space. That's what a wave function is. And so as soon as you sort of recognize that, you know that, you know, it can be connected to some basis, right? That it can be decomposed into, you know, it can be interpreted as a sequence of complex numbers, a linear decomposition, if you want, right, into some basis. And that's how all these things are connected. And then you can sort of try to build quantum mechanics as an entire whole, right? That as opposed to like a patchwork of different concepts. They're all the same kind of, they're all under, it's all, you know, it's all linear operators acting on a Hilbert space. So that's all of it. And I think that's a helpful way to think about things because it sort of helps bring it all together, as we'll see. And it'll be more obvious when we do examples, I guess, but I think it's important to establish these concepts first. Okay, well, that's all I have for class, but yeah, and then next time, you know, we gotta get to spectral decomposition, but in recitation, we'll talk about Fourier transforms some more, and maybe some more on, you know, integration by parts and you know, working with these functions. I hope you've seen some of this before, but I'm happy to review it too.
Yeah, review is necessary.